last review, I went through and did each problem. There was a little bit more work involved with this one and some of the problems, so I want to make sure that I could kind of show you the work and then talk through how to do it. So we're going to go just question by question. I'll show you the answers here and then talk through how I did each problem. And again, for sake of this not being, half hour long, I'm going to go kind of quick. So if you need more clarification, I'll be at school early on Thursday. You can come and ask certain questions. Alright, you'll see already that in my graph I made a mistake because when I read it first, I said I read it as the surface first moves up. I don't know why. Maybe my eyes skip down here, but the surface first moves down from its normal position. So normal position is at the x-axis, and if it moves down first, then your sinusoid is going to be heading down and then up. They tell you the period is 54, and so I know one cycle's completed in 54. I don't start at a high point because you start at like baseline, just the baseline, and then you go down and up again. And then I just marked off the middle, and then the quarter points for part B. At what time will the surface be farthest from its normal position? Well, it's going to be furthest from its normal position. I read that as, since it is asked for the times, I read it as the first time it's going to be positively further from its normal position, which would be at 40.5, where the high point is. For C, write a particular equation expressing displacement. The amplitude they tell me is 50. I think that was something that they told me up here. Yep. And then it's negative because my sinusoid has been flipped, because I head down first instead of going up. To find the period, you take the B value, you take the period, which is 54, you flip it, multiply it by 2 pi, that gets you pi over 27. So that's my B value, times x. I have no displacement because at time equals 0, that's when my sinusoid started. Part D, what's the displacement at t equals 21? All I did was plug in 21 for x and got that out. And then for E, what are the first 3 positive times at which the displacement is at negative 37 meters? That's a y value. So what I did is I plotted that as a y value, so straight line, and then plotted my function also, and I looked for the 3 spots where it intersected. So where my curve intersected that straight line of negative 37, those were my first 3 time values. Alright, for question number 2. Now, this one you had to use a property first, because you can't solve this algebraically, which it does say to show all work algebraically. You can't solve it algebraically unless you, where was I going with that? Oh, unless you have the same function. So replace sine squared with 1 minus cosine squared. That's the Pythagorean relationship. Distribute the 5 through, get it in order. So basically it's going to look like a quadratic. Then you solve it like a quadratic, and I actually punched out my 2 answers. And notice I didn't use the cosine because that's technically like my variable, so I just used the coefficients. Once you get your 2 answers here, that's what cosine is equal to. So then you set up 2 different equations. Cosine x equals 0.834, cosine x equals 0.239. And then you take the arc cosine of both sides. And there's the general solution. I put the positive version in to my calculator, the negative version into my calculator. Same thing down here, took the arc cosine of both sides, put the positive version in, put the negative version in. So you have 4 different equations that you're working with. But when you go to your table, and maybe I still have it on my calculator. Hold on a second. No, I don't. When you go to your calculator, you'd have a y1, y2, y3, y4. And remember, like the 0, 1, 2, 3, that stuff you're putting in represents how many revolutions you're going. So I just picked out the values or the answers that fit into my 0 to 2 pi scenario. Okay, skip it. This one, you first had to use a property. I rewrote this with 2 times 2 sine x cosine x, because then that looks like the double angle property for sine. And then I divide both sides by 2, and then I took the arc sine of both sides. Then over here, I wrote the general solution for both. That 1/2 has to be outside the parentheses for the general solution. I put it in my calculator just like you see there. And then again picked out the values in my table that fit into that scenario from 0 to 2 pi. Excuse me. For question 2 and for question 3, if you didn't get these answers but you have some of the same work, maybe come in and check with me in the morning to see if you put it in your calculator correctly, because we want to make sure you can do that correctly. Okay, for number 4. This is just dealing with a right triangle here. We're supposed to find theta. You're given the opposite side and the adjacent side. So I set up as a tangent problem. To find theta, I'm going to find tangent of theta equals 5.7 over 8.3. Take the arctan of both sides, but because we're working in the triangle, I only really need the one answer, so I didn't bother with the general solution. I just wrote down my degree value there. So theta is 34.479. And then it asks, how far will the beam travel through the patient's body before reaching the tumor? Well, that's going to be this straight line distance here, but because this is a right triangle, I can use the Pythagorean theorem. And so that's how I got the 10.069. Okay, I know I'm going fast, but some of these are going to take a little bit more time to talk through, so I want to make sure it isn't super long. Okay, part A. Small pulley has diameter, rotates at 100 revolutions per minute. We're supposed to find its angular velocity in radians per second. All this part is asking you to do is to convert units, because they give you revolutions per minute. That is an angular velocity. It's how fast the angle is turning every minute. So we set it up to get rid of the minutes. I'm going to multiply by 1 minute over 60 seconds. And then to get rid of the revolutions, 1 revolution is to 2 pi radians. So minutes will cancel, revs will cancel. I multiplied across the top and the bottom. You're getting that value for your angular velocity. For part B, find the linear velocity of a point on the rim of the 10 centimeter pulley. You gotta be careful here, because the 10 centimeters represents the diameter, not the radius, and that's actually a mistake I made right off the bat, as I put a 10 in instead of a 5, but then I caught it. So to find the linear velocity, use the equation V equals R times omega, where the omega is your angular velocity. And so since this is the angular velocity of the small pulley, and that's the pulley that I'm looking at. Hi. It's okay.
I forgot that your weight and your thing are technically to YouTube.
Yeah.
So I can't watch it on the library computer.
You need to ask Ms. Hartman if she'll sign you in to a computer next to her, because I know that she's done that for other students, and then you can just access YouTube.
But she almost didn't let me and Amy go into the library. Denise had to call her and tell her I wasn't there.
Well, just because you're supposed to have a pass, and since you're not technically supposed to be here, and since always. So, just ask her.
Right.
Just ask her. I'm sure she would. Yep. Alright, I forget where it was. Oh, anyways, you multiply them together, you get a linear velocity on the small pulley at the rim of 52.36 centimeters per second. Then for part C, find the linear velocity of a point on the belt connecting the two pulleys. Well, the belt can only be going as fast as the rim on the smaller pulley is going, because that pulley can't go faster, linear velocity-wise, like it can't cover more distance than what the belt is traveling. So actually the belt has the same. And then for D, find the linear velocity of a point on the rim of the large pulley, which has a diameter of 30 centimeters. That's actually still the same thing. They each have, because they're connected by that belt, they each have the same linear velocity. For part E, we're supposed to find the angular velocity of a point on the rim. Well, because this wheel is bigger, it has more rim, so the distance that the belt has to go, like the belt has to take one trip around that, it's going to take this, it's going to have to turn slower than the small pulley, which has to cover the same distance as the large pulley, but probably has to turn many, many more times because it's so small. So we use the same equation, V equals R times omega. We know the V for the big pulley is 52.36. The radius is 15. And then we have to find omega. So I just divided 52.36 by 15, and I get 3.4 radians per second. And then find the angular linear velocities of a point at the center of the 30 centimeter pulley. Angular velocity is going to be the same thing anywhere on the pulley. So since the angular velocity at the rim is 3.49, at the center it's also 3.49. linear velocity at the center, you're not covering any distance if you're at the center, so we have a 0 centimeters per second speed at the center there. Okay, for this one, question number 6. This is a problem that's already set up. It's already been factored for us. We know that because there's parentheses, and then you have this greatest common factor that's been pulled out. And it's set equal to 0. So we're going to actually go from this and solve it like we would like a quadratic that's factored, where you take each factor and set it equal to 0 and solve each separately. So I'm not going to go through this again since we've kind of talked about how to put in our calculators, but notice, oh, I missed something there. There should be an X, or an N. When you put it in your calculator, you're going to have 4 different equations. 1/2 of the plus, 1/2 of the minus version, and then the plus version and the minus version of that equation. And then you just want the answers between 0 and 360, which end up being those answers there. Okay. For this question, you draw on the sinusoidal axis, varying sinusoidal axis. The amplitude for that varying sinusoidal axis is 2.5. It's a cosine because it starts at a high point. Then to find the b value, take the period, so which is 4, you flip it, so 1/4, and multiply by 2 pi, which ends up getting 1/2 pi, and then an x. Then you look at the smaller sinusoid, and I counted how many, so 1, 2, 3. I did that until I found out there was 10 full cycles of the smaller sinusoid that fit into one large cycle of the other. The amplitude you can see of the little one is 2.5. It goes up 2.5 and down 2.5. And since 10 cycles fit into one cycle of the larger, 10 times 1/2 pi gets me that 5 pi x. Okay. Okay, for this one here, I'm just going to more talk through how to set it up. If you're given a value and you're given the quadrant it's in, you draw a reference triangle. We know cosine is x over r, so I know my x value is -3, my r is +5, and then I have to find that length there. And so I solved using the Pythagorean theorem and found out that y is 4, but I had to make it a -4 because of the quadrant it's in. Then that angle there is A. And 1/2 of A would be somewhere in the second quadrant. That's going to come into play here. Then you have to find sine 2A, cosine 1/2 A, and tan 2A. So you'll notice the first thing I did is I found it on my property sheet and I wrote down what it is property-wise. And then I replaced sine A with the value that it represents. So sine of A is opposite over hypotenuse, so -1/4, or sorry, -4/5. Cosine of A, they've already given me that value, so I'm going to replace cosine of A with what it's equal to, which is -3/5. And I just multiply them together. Here, I picked the negative version because cosine is negative in the second quadrant where my 1/2 angle is. Cosine of A gets replaced with -3/5, and then all of this is just simplifying. And you should, or you could get negative square root of 5 over 5 if you wanted to rationalize. Same thing with tangent. Tan A here is opposite over adjacent, so -4 over -3, which is 4/3. And then I have to square the 4/3 on the bottom, and then it's just simplifying from that point to get -24 over 7. Okay. This one. I used law of sines for the first question, law of cosines for the second. The work is pretty self-explanatory. I guess the reason I used law of sines here is because I had all my angles. I found the 35 by adding up these two that they gave me, subtracting it from 180, which I found out was left, and then set up 2 law of sines. It's quick. And here I'm just looking for the angle, and I'm given all 3 sides, so that's why I used law of cosines. And then to go from here to here, I just took the arc cosine of both sides. I know that we're pretty solid on this, so I'm not going to spend a whole lot of time on it. So you might want to pause it because I'm about to flip the paper. And pause. Alright, for this one. This is more of a concept question. Suppose someone tells you that ABC has those sides. Explain why there's no such triangle. So you can explain several different ways. If I ask you to explain algebraically, then you need to show me by like trying to find an angle using law of cosines or something and then show that it doesn't work. That's one way. You could also say that you can't possibly have a triangle built like that because 6 plus 2 is way less than 14. Like you wouldn't even be able to take the side of 14 and line up your other two sides and have it be complete. So there's no way that they would connect if these two sides came up off. Like they would be short because you're missing. So that's like another way to explain it. Again, algebraically, you'd have to use either law of sines or law of cosines and then just show that it doesn't work. Kind of like Hero's formula here. If we try Hero's formula, when I found S, and plug everything in, you'll notice I get a negative number underneath the square root. Because you get a negative number underneath the square root, that means there's no area. So it's impossible to find an area of that triangle because that triangle is an impossible triangle. So I know that's a hurried explanation, but I think you guys can catch on to that. And then number 11, evaluate the following limits. That is factoring and dividing out, and then substituting back in. Again, not taking a whole lot of time here. Okay, back page. Okay, we're going to spend a little time on this. I think I'm doing okay on time so far, but I want to finish up here in the next 2 minutes or so. To find the average rate of change, you're basically setting up the slope formula here. And they give you two specific t's to start with, so 2.1 and 2. Plug 2.1 into my function to get that number. Plug 2 back into my function to get that number. And then just divide it out to get that. Your units are millimeters squared, which represents the area, changing every hour. For part B, you're supposed to write an equation for the average rate of change from 2 hours to t. You set it up the exact same way, but instead of having a 2.1 to plug in, you just have a t to plug in. And a of t is that function there, so we're going to replace a of t with 200 times 1.2 to the t minus 2.88, because it still wants me to have 2 be the focus point there. So a of 2 is still 288, and on the bottom t minus 2. Now let me talk about where you would use this. In a problem, and possibly even the problem on the exam, you have to take this concept here of this r of t, this function that represents the average rate of change at any point, and I would ask you to evaluate maybe at 2.01, 2.001, 1.999, 1.9, and either you do this 6 times, or if I've asked you to write this, which usually I have at that point, you put this function into your calculator, and then any of your y values in your table will represent the average rate of change. So like if you put this into your calculator and your y equals, and then you go to your table and you put in 2.01, what it's doing is it's physically putting in 2.01 for t here and here, and then the answer you get is an average rate of change. The benefit to doing it this way instead of just punching out the numbers every single time is because it cuts down the work tremendously, especially if you have to test multiple values. Okay, and the last one, find the integral of the function using a function. Find the integral of a function using a function. Oh, shoot. I didn't give you the right example for this. Sorry, this is like using a table, but we can kind of talk through it. So this would be like if for this one, it'd be like if I gave you, I don't know, I guess we'll use the same thing we did before. If I gave you a function like that, and then gave you an interval, let's say I wanted you to find the area under the curve between 1 and 4, and I wanted you to do 10 trapezoids. The space between 1 and 4 is 3 spaces. You find that by 4 minus 1. And then if I want to fit 10, you take 4 minus 1, which is 3, divided by 10. So 0.3 would be the change in x value in that case. Now I hope you didn't lose me. This is a completely different example here than this one here. This shows you how to set up the trapezoid rule based on a table, but I just realized I'm asking you to use it in a function, which is different. So that would be your change in x And then in that case, you'd have 1/2 of 1, if 1 is your first value you're looking at, plus, f of 1, plus f of 1.3, plus f of 1.6, plus f of 1.9, plus f of, and you get the point. Every x value that you're plugging in for each trapezoid is 0.3. Since you're changing x to 0.3, it's 0.3 above the other one. And then your next step would be to plug in 1 to the function, 1.3 to the function, 1.6 to the function, 1.9. So then all of these values become y values, and then it's just punching them out. In this case here, it was just punching out the y values basically, because the y values were given to us in a table. But you have to be able to do it with a function. Okay, I think that's it for that one. Again, especially that one, if you feel like you need more help with that, come in and talk to me in the morning.